So hi, Pete Shersby here from Make or Repair, and finally the long-awaited repair of this Hewlett-Packard 435A power meter. It's taken quite a lot longer than anticipated to do the repair because of supply problems, and also because a new fault developed during the repair itself, which threw a bit of a curveball. But here we go. Looking just at how well it was performing, and things weren't too bad. So it first of all had problems, a couple of physical problems. The switches themselves, one of them wouldn't move. The meter was all messy and really needed dealing with. Now, I wasn't really willing to fund the complete replacement of switches and moving coil meters. So I looked to do some repairs there, and that worked out okay. And then I moved on to do some tests on the performance. Pretty much always, the first thing you do is just check the voltages. They should have been 12 volts, they were plus minus 12.2, so that was fine. And then I checked the reference output, which should be 0 dB or 100 milliwatts, and that was bang on to within about 0.2%. So I was happy there. So the process then really is seeing what else is wrong. Well, a couple of things were wrong. One is that some of the ranges were over-reading and under-reading, and the second was that the zeroing wasn't working quite right. So the process for that really is to use the service manual and start tracing through the circuit from start to finish. And the service manual is really good for this because it does actually include a lot of reference waveforms and voltages and test points and things like that, unlike modern service manuals, it has to be said. So I was able to start tracing through, and things were looking pretty good until all of a sudden I hit a sort of, hang on a minute, that doesn't make any sense moment. Test lead. Okay, minus 10.36. So not a million miles off. Oh, I say. And that is all over the shop. New 741 op amp in. That has solved the problem that the voltage is all over the shop. Now the reason that it's clipped at minus 10.832 volts is simply because it's a times 7000 amplifier and it's got a volt going into it, so 7000 volts, that's not going to happen. This actually, the test point should mention that you actually need to zero this. You need to have a working sensor on the front in order to get the 0 volts on the front end of this amplifier. And then what should happen is we then get an offset which gives us the voltages we need for the capacitors to create the 0 volt feedback loop with the sensor. To work on this on another day, and found a bit of a problem, which is that some of the voltages that were fine before are no longer right, and in actual fact the power supply is not giving the right power anymore. So I've taken the board out, I've connected an external supply across the bridge rectifier down at the bottom there, and I'm feeding in nearly 70 volts in fact, to drive this circuit, which is the correct voltage. And what I'm going to do now is do some diagnostics and see if I can find out what's gone wrong. So this circuit is getting about 22 volts and gradually rising, and then it's okay, and then when I reset it, it's all problem again. So here we go. Let's turn on the power, and the voltage is rising really slowly. There should be about 24 volts. So I know what you're thinking, it's the capacitors. Now the two capacitors next to my probe are actually replaced. They're at the output stage from the power supply, and I have disconnected the power supply from the subsequent circuit. There's a couple of jumpers on the board for that. So this is the pure output from the power supply. And I've had a look at one or two of the capacitors, they look okay. And in truth, even if they were a bit leaky, I don't think they'd be affecting things a huge amount, but it is a capacitive-like problem. So I'm going to work through the circuit and see what I can figure out. What else do I need to say about this at the moment? Not a lot. I will take some of the capacitors off later and test them independently, and I probably will replace a lot. So rather than showing me going through lots of transistors, taking off boards and things like that, I decided I would just bring the schematic up on the screen and talk about what I did to find the faults in the power supply. So I guess first things first, let's just add a few little extra bits to this. So just here we've got the plus in, and down here we've got the minus in from the bridge rectifier, and we've got a bit of a battery switch circuit up at the top here. Okay, now mine has not got a battery in it, just to be clear on that point. Okay, and our symptom is that the voltage is going to about 22 between test point 9 and test point, come here, 10. Okay, and it should be 24. So essentially, this line here, here's our input from our bridge rectifier, and it's going straight across here to the output. Here's our negative. It goes through this transistor regulator, and that's going to regulate to minus 24 volts versus this top line. So the difference will be minus 24 volts, and we're going to split that to get 0, and that is how we get 0. If we follow the, just here, R63, R64 form a voltage divider that halves whatever we've got. So that gives us our 0 volt, and that's our reference voltage. So of course that's always 0 volts because it's kind of our reference voltage, unless this goes wrong. And then we just buffer that with this operational amplifier. It's just a 741 op amp, and it's feeding into this. This is shown as a push-pull pair, but in actual fact mine has a circuit change to it, which means that this resistor here does not this transistor here does not exist at all. So you know, this is just a current amplifier. It's just giving us our current that we need for our 0 volts. So this is a differential amplifier, and you can see that one end of the differential amplifier is connected to our 0 volt, just here. The other is connected via this resistor to the bottom of this 12.1 volt Zener. And I know it's a slightly odd symbol, but VR4 is a 12.1 Zener. So it should be 12.1 volt. This junction just here should be 12.1 volts below the top line, and the top line we're saying is notionally 12 volts. Great. So I've got 12 volts below, I've got 0 volts here. So if those two things are not the same, then I will get an error term coming out of this differential amplifier down here. Okay, because that one is tied to ground, so to minus 12. So this is monitoring this 0 volts to make sure that 0 volts is actually 12 volts below 12 volts. If this regulator down at the bottom does not cause minus 12 volts versus the 0 volts to appear on that bottom line, then the divider isn't dividing 24, it's dividing, in our case, 22. Okay, which makes it 11 volts below the top rail. So one side of the diff amplifier is at 12 volts or minus 12 volts, the other side is at minus 11 volts. That's a difference of 1 volt. So it outspits that volt down into this part of the circuit. This part of the circuit then, that voltage error feeds into the base of Q16, and we take off the collector and feed that into the base of Q13, which is our follower. So Q13 will produce on its output whatever we've got on its base, with a difference of 0.6 volts, 0.7 volts, thereabouts. So if it's a bit high, that will divide out and give us an error in one direction. If it's a bit low, it divides out and gives us an error in a different direction into our differential. And essentially the differential will drive this voltage up and down until it is correct, at which point this transistor will be this feedback circuit through the differential amplifier will be stable. Now, I'm quite surprised, to be honest, that HP didn't do that with an operational amplifier, because that's what they've done pretty much everywhere else in this. But they've obviously decided they just fancied popping a pair of transistors in. So this isn't too bad to test. Obviously we just have to test VR4 to make sure we've got 12 volts. That's fine. I did do a few tests around some of these other transistors as well, just to make sure that there was no problem there, that they weren't sucking out current. And I also tested the voltage across C22 to make sure that that was stable, and it's actually about 70 volts, because this is a very high voltage input, partly because it has to charge a big battery. Okay, so those are all fine to test. Now, since this isn't working, we should expect to see a I've just got to find my mouse again, thank you. We should expect to see error on here and here, which is proportional to whatever error amount exists, and we do. So as the voltage gradually creeps up towards 24 volts, the error on those 2 points gradually creeps downwards until it's nothing. So it is driving this correctly. Now, I did suspect maybe this capacitor here, and I also suspected this capacitor here, that this might be leaking and causing me a problem with the voltage on VR4, but didn't seem to be doing so. The same with this. I replaced this with a temporary capacitor, just to be certain. No difference. And my voltage here was low, which is correct because, of course, I've got an error term. So really, then there are only 2 more candidates, which are these 2 transistors. So I took out Q16. I didn't have a diode replacement for it, but there's nothing special about Q16. It's just a few milliamps at, okay, potentially quite a few volts, maybe 30 or 40 volts if things are really bad, just going into the base of this transistor. It's nothing. It's got a big resistor up here, 26k, so the amount of current through that is small. So I just stuck, went to my scrap bin, grabbed a NPN transistor. I think it was 45 volts, 1 amp, in a TO92 case, bent the legs and stuck it in the circuit, and it works fine. So that's it. That was that transistor that was faulty. Now, I know lots of people are thinking, oh well, the capacitors are going to be in a terrible state, all those electrolytics. These are not electrolytic capacitors. These are tantalum capacitors, with the exception of C22, the big input one. So that one there is an aluminium electrolytic. All of the other big capacitors are tantalum, and they are expensive. And in total, I'm going to have to replace quite a lot in the whole circuit, because it's not just this, the other places that I'm going to have to replace them. What I've done is popped them out, tested them. So I put them in the LCR meter and checked their capacitance, their ESR, and their D. The word won't come to me at the moment. Dissipation, thank you. They actually all looked okay. And then I actually decided I would measure the leakage specifically, and about half of them at that point failed. They shouldn't have much leakage, a few microamps, it depends on the voltage, but a few microamps of leakage is all you're expecting, and 1 or 2 of them are actually leaking milliamps. They're acting a bit like resistors. So what I'm doing now is just setting up to go through the alignment procedure, and really this is a case of looking at the various test points, making sure the voltages are in range, adjusting a few trimmers to bring them in range, and then the manual actually documents a series of settings and adjustments with the trimmers to ensure everything is correct. So just running through that, and then I'll give it a final performance test, well, maybe final performance test once that's done. So I've tested the reference output, and that's now spot on again, happily. And I'm now going through feeding in some known signals and comparing them. Unfortunately, while the top end of things, so 20 milliwatts, 100 milliwatts, that sort of thing, 20 dB, sorry, I should say, not milliwatts, is fine. When I actually get to the bottom three settings, so 3 microwatts, so that's, what's that, minus 25 dB, minus 20 dB, and minus 15 dB. I'm starting to get some error, quite considerable error in actual fact. So I need to explore that and find out what's going on. We're pretty much there with this meter. We've just got this final little problem with a few of the ranges being out. I'm starting to tackle the problem that I'm reading a little bit low on some of the lower ranges. Now, I started off and I've just checked all these resistor sets on all the switches down here. There's another bunch somewhere else, a bunch here, another bunch here, and they all look absolutely fine. So I'm just applying a normal ohm meter across these, reading those readings. And what I've done next then is I've applied a full signal and I've measured it just here, 0.4, which is basically the output of the first couple of attenuators. Now, for each range, as long as I put a full range signal in, each range should read the same, and it does. When I come over here, I should read round about 0.2 volts. Again, on every single range, they should all be identical. Now, I'm actually not reading that. So to cut a long story short, the voltage must be varying somewhere. The likely place is on this next switch section, which has some capacitors, so that could well be leakage, and of course there could be capacitors elsewhere. So I'm actually going to take a moment now. I'm going to pop out all of the capacitors one by one. I'm going to test them, and I'm just going to work my way through all these tantalum capacitors, seeing if they're in range or if they're actually leaking. There is a good possibility that some of them are leaking, and I'll have to do my tests quite carefully to differentiate those. I suspect most of the capacitors will be okay, except for leakage current. So I'll measure it on my capacitance meter, and also by putting a voltage through and measuring the leakage current using a sensitive multimeter. Okay, so I have been testing the capacitors, and so this is the electrolytic. It's not too bad. It has drifted quite a long way in its value. It's ESR, it's not leaking, but I've decided to replace it anyway, just have that extra bit of capacitance, and I had got the capacitor, so why not? I've got 22 and 68. These are in pairs, these capacitors, and one out of each pair had failed, and I figured I would actually just replace the 3 pairs, 6 capacitors. Most of them are just in power regulation, so I'm just going to put electrolytics in for those, which will keep the cost a bit more sensible. Now, in the power switch as well, sorry, the range switch I should say, which is extremely difficult to get at. In here, I think either 4 or 6 capacitors. Now I can get access to 2 of them. I've popped them off, I've tested them and popped them back on just so I don't forget where they go, and both of them have failed. So I'm going to replace all 4 on that switch, and actually it's those 4 capacitors on the switch that I suspect are the problem. Taking a quick look at the diagram, this is the section of the range switch just before the DC amplifier. So we can see several capacitors in series with resistors, and they're all going down to ground. So I've taken off capacitor 2, which is 15 microfarad, and I've tested it, and it is passing DC current. So essentially, I think that's happening on all of the ranges, and what's happening is it's just pulling the value down towards ground. Ouch. So after taking off one entire side of the frame, I have managed to disconnect most of this side, and the front has now become loose. Enough to manipulate a small amount. Hopefully that is going to be sufficient for me to get in here and replace a few of these components. I just have to be careful not to dislodge any of these wires, otherwise I am going to be struggling to find where they're supposed to be. So now, if I've got replacements for these capacitors, I am just going to drop them straight in. So that goes in the middle of that resistor there, and that temp there. So this is really tricky. The inner ring in particular had two on it, and they were very hard to change. So I just sped this up and just showed replacing one capacitor. But it took me about an hour to replace all 5 capacitors. Okay, so I've got it all back together. No screws left over, which is always a bonus, and not missing either, which is also slightly miraculous. So I've got it connected up to the calibrator. I haven't spent a long time just tweaking the calibration at all. All the knobs work, so this is all good. Mains is on. Everything appears to be working. We've got the needle over where it should be, pretty much. Oh, it means a hair's whisker out, but I'm just not going to bother adjusting it this time. Okay, 5. This should be minus 10 now. Lovely. But, yeah, nice. It's back to 0 on that, so that's fine. That's what it should be. Turn up to 10. We're back down to 5. Back up to 0. Lovely. Back down to 5. Back, yeah, just a shade over 0. So, okay. That's 15. On to 20. Yeah, down to 5. Yeah, so this just needs its amplifiers realigning. So that's all looking very good indeed. Just go the opposite direction now. This is minus 5 on the money. And they go minus 10. Good. Lovely. Oh yeah, and we're hitting 0. So this is the piece that is heavily using those capacitors that I just replaced. Now, those capacitors are probably quite hot and the resistors around them are hot, so don't expect that necessarily to exactly hit 0. But it's not a long way off which it was before. Lovely, look at that. Okay, so our power meter is finished, all reassembled. I'm just going to give it a quick sanity check. So I'm going to connect this to a tightly calibrated 0 dB. Turn that on, that'll be good. Yeah, we're just a bit over. Let's wind ourselves back. Lovely. Okay. So that is a tightly calibrated 0 dB. I should now be reading minus 0.316 apparently. And I am reading minus 0.3 and a tiny bit that I can't make out, of course. Let's raise ourselves up to 5 dB then, and turn that down to 5 dB first. So there's 5 dB, and that apparently should be 4.778. So I'm making that about 4.8, which is pretty damn good. at 6. So we're within about 0.2, 0.3 dB on every single range. Excellent. Okay, so this has been quite a vexing repair. Started off with the physical side on the front. That went pretty well, cleaned up all the switches, the connections, etc, etc. And it seemed to be going well. Checked the voltages on the power supply, they were all right, and started diagnosing one or two problems, which were that the microwatt settings were a bit iffy and the zeroing wasn't working. Unfortunately, that meant I had to order some parts, which I had to wait a long time for. And then when they arrived, I put those in and then discovered that the power supply has subsequently broken. Now that took a little bit of time to diagnose because, of course, I wasn't really expecting something else to go wrong while I was repairing it. So it led me down a few blind alleys, but I got there eventually. I did replace the meter scale, basically scanned the meter scale on a flatbed, retouched it all in Photoshop, printed a new one, stuck it on the front. The first one actually failed because it was glued on, and although I'd rubbed it down with sandpaper beforehand, the substrate was so bad that it actually lifted off anyway. This one is restuck pretty much basically onto the bare metal. Power supply problem was ultimately down to a transistor. And then I started checking all the scales, still had some problems with the microwatts, the last 3 microwatt scales. And I decided that it was probably down to capacitors. And I popped all of the tantalum capacitors in the entire device out, tested them, and replaced anything that had high leakage. I suppose the point to make there is that when you pop the capacitor out, pop it in a capacitor meter, it measured absolutely fine. It was only when I actually connected it to a microamp meter in my multimeter, put some voltage through it, maxed the voltage out for each tantalum, that I was able to measure that the leakage was far too high on some of them. Anyway, I managed eventually to source some tantalum capacitors. These are Axlial metal can tantalum capacitors, very difficult to get hold of, very expensive, which is why I only replaced the ones that needed it. But yeah, this is about 50 years old, and it's probably good for another 50 years now. So hopefully you enjoyed that. If you did, thumbs up please. If you haven't subscribed, please go ahead and subscribe. That really helps. And I'll see you next time. Take care.